maybe you can start introducing the seminar. Okay, so good morning or good afternoon, everybody. So I'm delighted to welcome you to the first SNAPP seminar of the academic year 23. So my name is Céline Comte. I'm a researcher at CNRS in France, and so today I will be your session chair. And so the fall 23 season of the SNAPP seminar will be organized as follows. Regular talks will take place every 2 weeks until December 4. And then on December 11, there will be a special seminar that we call a lightning session, and for which we'll send you more details later. And so for today, it is my pleasure to introduce the first speaker of the season, Isaac Grosof. So Isaac is the Tenenbaum postdoctoral fellow at Georgia Tech. Their research interests lie within queuing theory, with a focus on scheduling, multi-server systems, optimal policies, and heavy traffic analysis. Before joining Georgia Tech, they received their PhD in computer science from CMU in 23. And after Georgia, they will be a postdoc at UIUC starting in spring 24, and then an assistant professor at Northwestern University starting fall 24. Their work has been recognized by the Informs 22 George Nicholson Award, as well as multiple Best Paper and Best Student Paper awards at Sigmetrics and Performance. And before I give the floor to Isaac, I should just mention that you will soon receive the link to the slides presented by Isaac in the chat. Isaac, please go ahead.
Thanks for the introduction, Celine. Thanks everybody for being here. So today I'm going to tell you about a new technique that I've come up with my collaborators called relative arrivals, which is a new drift method for handling systems with time-varying arrivals. So my name's Isaac, and this is joint work with my collaborators at CMU, Yige and more Harchol-Balter. So the kind of systems that I'm interested in studying are systems with Markov modulated arrival processes. So what does this mean? You've got some arrival rate. Maybe there's some low baseline load where most of the time there's not too many jobs, but occasionally you have some bursts of arrivals. So maybe your product got really popular, so everybody's interested now, or there could be all sorts of reasons this might happen. And this is a very common thing to occur in all sorts of application areas. Might be computing, might be healthcare, might be retail. And these bursts could make up a significant fraction of your overall arrival rates. So the question is, can we understand the performance of a system like this? As a concrete system, in this talk, I'll look at the two-level arrival queue. So we have a normal queuing system, and we have two possible arrival rates, some high arrival rate and some low arrival rate. And we'll switch between them according to some rates, alpha high and alpha low. And then we'll just have a fixed completion rate. To visualize this, our arrival rate will look like this sort of step function, switching between the high arrival rate and the low arrival rate with exponential periods of time in each one. And we'll call the overall average arrival rate lambda. Now, the performance question that I'm interested in is, what's the mean queue length, E of Q? Very fundamental question in the system. And the result we're going to come up with is actually going to be widely applicable. So not just for this two-level arrival system, but applicable to all Markov modulated arrival processes. And we'll see as we go through the talk, can be generalized even beyond that. Okay, so what's known about this two-level arrival system? So one direction people have studied it is with sort of computational methods. And what I mean by this is you come up with a provable result, but that result doesn't immediately let you say anything about mean queue length. And then you have to do some extra work, usually some computational work, to actually pull out a concrete number. So this would include methods like generating functions, which have been used on the system for a long time, or matrix analytic methods. Okay, so then what about symbolic results? Okay, One direction that there's been symbolic results is in heavy traffic. And there is a semi-closed form result in heavy traffic. It'll tell you the queue length, but not in a way you could actually write down a symbolic formula for it. This was done by Mu and Magluri in 2020. It's somewhat related to our results, but our result applies well beyond heavy traffic and gets you concrete symbolic results. And then there have been structural and monotonicity results saying, as you adjust alphas or as you adjust lambda, performance moves in this direction, but it doesn't give you concrete, specific formulas. So what I'm really interested in is a specific formula for mean queue length. And for that, there's been no prior results. And that's going to be the goal of this talk. Okay, so here's how the talk's going to go. I'm going to give you some background on the drift method. I'll tell you what it is and how it works. And then I'll tell you about our new idea called relative arrivals, which allows us to apply this drift method to these time-varying systems, to these Markov modulated systems. And the result we get will be a mean queue length formula, a simple symbolic formula to bound mean queue length very tightly for all Markov modulated arrival rate systems. And I'll illustrate it for the two-level arrival process in particular. Okay, so what is this drift method? The basic idea is pretty simple. You choose a test function, which takes as input a state of the system and gives you back a real number. So in our two-level arrival system, the state of the system is the queue length and the current arrival rate. Next, you use the instantaneous generator to find the drift of this test function. And the drift is just the instantaneous rate of change of the test function. And it's defined like this. We look at the difference in the value of the function between 2 points in time that are, and we look at the limit as those 2 points in time go to 0, take the expected value of that difference, and find its rate of change. So this is basically the stochastic variant of a derivative. And the key fact about the drift is that the time average value of the drift, so the expected value of whatever formula you get here, is in fact 0 for essentially any test function f. And this drift is not too hard to calculate if you just know all the rates at which events like arrivals and completions happen in the system. So this will give you a lot of useful information about the behavior of the system. And if you choose the right test function, you can find out whatever you're looking for. In particular, by choosing a function that's quadratic in the queue length, we can get information about the mean queue length, because this operator is basically like a derivative. So we want to look at the queue length squared to find information about the mean. So to demonstrate how this method works, I'm going to walk through it for a very simple system, the MM1. So the test function couldn't be simpler. It's just the square of the queue length. And we can just explicitly calculate the drift of that function by looking at the effects of arrivals and completions. And what you'll notice is that this drift is essentially a linear function of the queue length. Okay, so you have the queue length, you have some constant multiplier, constant addition, and then a little adjustment when the queue is empty. And the reason that this drift is a linear function of the queue length is because the queue length itself has constant drift. It's up to the edge case when the queue length is 0. And these this linear function and constant are very closely related. The term, the coefficient of the queue length and the drift of the quadratic function is the same as the constant drift of the queue length. So when we have this fact and we look into the time average drift of this test function, we find it's given by this formula. We've got our linear term becomes a mean queue length term, and everything else is simple to characterize. This probability that the queue is empty, we can characterize using this test function. So by combining everything together, we find an exact formula for the mean queue length. Now, this is the MM1, so characterizing its mean queue length isn't too hard, but this shows you the general structure of the drift method. The key idea behind the drift method is, well, the queue length had constant drift. So its square had linear drift, so we can find the mean queue length. So in other settings, we might have some more complicated drift function, but if we're trying to characterize mean queue length, there'll still be some quadratic function of the queue length. So for instance, in max weight, in a setting like an N system or a switch, you might use the sum of the squares of the queue length of each class of jobs. Or if you had non-trivial job sizes, you might use the squared work in the system, so their total size, rather than the squared queue length. And there's many more applications of the drift method, and people use increasingly fancy functions to get different performance metrics and tighter results, but this is the basic concept. Now, the challenge under varying arrival rates is that right from the beginning, the queue length doesn't have constant drift. In a time-varying setting, the drift of the queue length would be whatever the instantaneous arrival rate is, minus the completion rate, and then the correction when the queue length is empty. So it's basically going to jump up and down the same way that our arrival process jumped up and down, our arrival rate jumped up and down. And the problem with this is that a simple test function, like the square of the queue length, is not going to give useful information about the overall mean queue length. It'll be mucked up by the fact that this isn't constant. So that's where we are. That's the background on the drift method. Now, let's talk about this new idea of relative arrivals. So the idea here is we want to smooth out the drift of the queue length. And to do that, our test function is going to need to incorporate the current arrival rate lambda. So our plan is going to be to find some correction function, delta of the state of the arrival process, such that the queue length plus that correction has constant drift. If we're able to do that, then the square of the corrected queue length will have linear drift, and we'll be able to find the mean queue length. So now let me tell you about our new idea, which I call relative arrivals. So relative arrivals are defined as follows. It's the limiting difference between the expected number of arrivals starting from state I and going up to some time t minus the long-term arrival rate. This will be easier to visualize if I show you a plot. So here's a plot. On the vertical axis, we've got the expected number of arrivals. On the horizontal axis, we've got a point in time. And here's some concrete setting of our arrival process. And here's what things look like. We've got some long-term arrival rate. That's just a straight line. And then in comparison, we've got the number of arrivals up to time t if we start in the high arrival. So you can see this initially grows very quickly because jobs are arriving fast if we're in the high arrival rate. But as time goes on, there's a chance we switch to the low arrival rate, things will equalize out, and eventually jobs will just be arriving at the long-term rate. Okay? And similarly, we could start at the low arrival rate, and it would get us this different curve. And in both cases, it'll be eventually linear with the same slope lambda. And this delta function, so delta high, will just be the gap, the vertical gap between these two curves. So how many more arrivals you have at a specific point in time t than you would at the long-term rate. And delta low will just be the same thing in the other direction. Okay, so this is relative arrivals. As an alternate perspective, you can also think of this delta as a relative value function. So you can think of delta I as the relative value function of the Markov reward process with reward equal to the arrival rate lambda I of t. So when you calculate relative value, you take the normalized reward, subtracting out the long-term rate, you look at its value over time, and you take the summation of this normalized reward. So this gives rise to a Poisson equation, which can be useful for actually calculating this delta of I, which is just your normalized reward over the period until you first have a transition, and then whatever your delta is after that point. So this gives rise to a system of equations for delta, which is very familiar if you've seen Markov decision processes. Okay, so we've got this relative arrivals object. What can we do with it? Well, the key idea is that relative arrivals have a very useful drift. What is the drift of delta I? Well, there's two terms in this formula. There's a lambda t term that contributes lambda to the drift of this function, and there's a expected arrivals up to time t that contributes a lambda I to the drift. And if you go through the formulas and calculate everything out, you find that the drift of delta of relative arrivals is just the long-term arrival rate minus the instantaneous arrival rate. And this is really useful because if you'll recall, the drift of the Q length was the instantaneous arrival rate minus mu. So if we add these together, if we use this as a correction, we end up with a constant drift. The drift of Q length plus delta I is just a constant with a little correction when the Q length is empty. So in particular, the square of that quantity, Q length plus delta I all squared, will have linear drift, and so we can calculate the mean Q length. Okay, so this is the idea of relative arrivals. I just want to check for a moment if there's any questions about delta I or how we're using it in the drift method. Okay, so we've got our idea of relative arrivals. What can we do with these? So our result is a mean Q length characterization for Markov modulated arrival processes. So our theorem says in a single server queue with Markov modulated arrivals and exponential service, we have this characterization of mean Q length. Okay, so let me explain what these quantities mean in this formula. So I'll write y as the time average steady state of the arrival process, and y arrival as the arrival average steady state of the arrival process. So what do I mean by arrival average? Basically, look at the system at every moment when an arrival happens and take the average state of the arrival process in those moments. So this is basically weighting the arrival process towards the states where arrivals are actually happening. So the formula we have here is we take the mean value of our relative arrivals in that arrival average state, and then that's the numerator in our familiar rho over 1 minus rho function. And just a reminder, rho here is lambda, the long-term arrival rate, over mu, the long-term, the completion rate. And then we have this extra term out the front here, which is the average value of the relative arrivals function in the state where the Q length, in states where the Q length is empty. Okay, and that comes from that little correction term to our drift function. So, what's the intuition behind this formula? Well, basically, imagine I'm an arriving job, okay? I don't just see like a time average instance of the system. Instead, I see an arrival average state of the system. And so the state of the arrival process I see on arrival is this y arrival state. And we know in order to smooth out the drift of our Q length, we have to add a correction term of delta of whatever the arrival state is. So that correction comes out to be the expectation of delta y arrival, and we end up with this formula for the mean Q length. So it would be the MM1 value if we didn't have this correction. That's what this gets us. And this formula we can almost exactly calculate in a concrete system with a concrete arrival process, like our two-level arrival system. So if we take our mean queue length, we can explicitly calculate this, this first term, which is the term that dominates, for instance, in heavy traffic. It's just going to be given by this formula here. And we can calculate this because we can calculate delta using our Poisson equation, and we can calculate the state y arrival just by solving the steady state of the system. Then to calculate the mean value of relative arrivals when the queue length is 0, we can almost exactly calculate that. The only part we don't know precisely is the probability, is the distribution of the arrival process in states when the queue length is empty. So that gives rise to a correction factor here, depending on what that probability is. Now this term up here dominates in heavy traffic, so we can exactly characterize the system in heavy traffic. And it only remains to bound these probabilities to understand the behavior of the system when we're not in heavy traffic. So we want to bound the system, we need to bound the behavior under an empty queue length, okay? So to understand this, there's two extremes that make sense to look at. One extreme is if we're switching very quickly between the high and low arrival rate. The other extreme is if we're switching very slowly between the high and low arrival rate. If we're switching very quickly, we expect that the state of the arrival process is going to be basically uncorrelated with with whether the queue length is 0 or not. So we'd expect the state of the arrival process to be, given that the queue length is 0, to be about the time average value, which we know explicitly. And this actually forms a bound in all systems, like for all alphas, the behavior when the queue length is empty, they're not going to be correlated with each other. The high arrival rate is not going to be correlated with an empty queue length. That much we can prove, and that's building on some prior results in the system. Now, at the opposite extreme, with slow switching, we would expect that if the queue length is 0, we'd almost never have the high arrival rate. And we can actually prove a bound to that effect if the arrival rate is larger than the completion rate. If the high arrival rate is larger than the completion rate, it means that, when we have the high arrival rate, we're in temporary overload. And so it should almost never be the case that the queue length is empty. And by looking at a transient overloaded M1, we can prove that and give rise to this bound on that probability. So putting it all together, we now have some very nice bounds on the mean queue length of this two-level arrival system. So let me show you what those bounds look like. And again, I'll give a concrete setting, but this time let me spell it out in a little more detail. We have some low background arrival rate of 0.2 compared to a completion rate of 1. So low load at baseline, but then occasionally we get these spikes of very high load, double what we can keep up with, transient overload. And the switching rates are going to be at this ratio where we spend 1/6 of our time in the high arrival rate and the rest of the time in the low arrival rate. And so this will give rise to an overall load of 0.5. So to be clear, we're very far outside of heavy traffic here. Okay, in the long term, we've got way more capacity than we need for the system, but in the short term, transient overload. And we'll vary the switching rate alpha and see what its effect is on mean queue length. So here, alpha will go anywhere from a pretty fast switching rate to a quite slow switching rate. So I'm going to start by showing you the bounds on mean queue length that we can prove. So and just to be clear, this is a log-log plot of switching rate versus mean queue length, just so we can see everything on one plot, one picture. So the lower bound just comes from, well, we know that the probability can't be less than 0. Plugging that into our formula, we get this lower bound on mean queue length. Then there's that slow switching rate bound that I showed you on the previous slide, and the fast switching rate bound. And I'm just showing you each upper bound in the switching rate regime where it's the tightest bound we have. And then when we plug in simulation, it goes right down the middle. So what you can see here is outside of heavy traffic, we have very tight bounds. They're tight, wherever you might want, and they become exact in the limit in both the fast switching and slow switching limits. Okay, so this relative arrival technique has allowed us to give very nice bounds on the behavior of this two-level arrival system. Now, as I mentioned, our result holds actually for all Markovian arrival systems, but we can generalize it even farther than that to systems with both Markovian arrivals and Markovian service. So our theorem is that in a single server queue with these Markov modulated arrival and service rates, we get this formula for mean queue length. So we've got that same relative arrivals of the arrival average state of the system, and then an extra term for the relative completions in the completion average state of the system, and that same plus rho that we've always had. And now we have a slightly more complicated additive term out the front that comes from the behavior of the system when the queue length is empty. This H function is just, it incorporates a completion rate weighted version of the relative arrivals and relative completions. But again, this is something we could very reasonably bound or work with in a concrete system. And this term out the front here, which is often going to dominate, we can calculate fully explicitly for any given system you might care about. As an example of the bounds you might prove, we can upper and lower bound mean queue length with an additive gap here, where that additive gap depends on the maximum and minimum values of the arrival and completion, relative arrival and relative completion functions. Okay, so we've got our bounds that hold not just for two-level systems, not just for Markovian arrival systems, but for all combinations of Markovian arrival and Markovian service. So what future directions can we take these things? So one direction is that the reason I originally developed this technique was actually to study a completely different system, the multi-server job first come first serve system. Now, to analyze that system, we had to come up with another different technique called reset. But when you put this work on Markovian service rate systems and that technique together, you can actually analyze, we were actually able to analyze the multi-server job first come first serve system. And that I'll be presenting at Performance 2023 in November. Another direction I'm interested in is analyzing the tail behavior of these Markovian arrival, Markovian service systems. Can we characterize, say, the transform of queue length? Can we get the limiting behavior of the limiting tail behavior in regimes like heavy traffic or high and low switching rates? Another direction I'm interested in is getting clean, simple formulas for the relative arrival function in systems with more complicated arrival processes, more complicated service processes. So this would sort of be an analog to product form results for the steady state distribution. This is a summation form result for the relative arrivals or relative service. Relative arrivals or relative completion functions, sort of the analog of that behavior. And finally, all this that I've discussed so far was for specific systems where there were no decision-making options. But there's a natural question of, could we find something like an optimal scheduling policy if we took a system like this and allowed the operator to, influence the completion process? Essentially, these techniques would allow us to reduce the question of finding an optimal policy, or at least a policy that was optimal up to low order terms, to just optimizing a finite size Markov decision process. Okay, so to wrap up, I looked at systems with Markov modulated arrivals, motivating example, the two-level arrival system. We defined this relative arrival function, the difference between long-term arrival rate and arrivals starting from a specific state. We got this very nice formula for mean queue length, and it gives rise to some very tight bounds on mean queue length. So that's what I've got to tell you about. I'd be happy to take questions.
So thank you very much, Isaac, for the very nice presentation. So are there any questions in the audience?
I have one. Can I ask one now?
Sure, please go ahead.
Yeah, please do.
It was a very nice talk, Isaac, and it's a very nice formula. It's amazing that such a nice closed form expression exists for this. I have a question. So you mentioned also Markov modulated service processes. Yeah. And so do you just add the relative service rate also to the expression and just square it, and that's what gives you the answer? Or what is the test function you use here?
Right. So the test function is just, so you take queue length plus relative arrivals minus relative completions, take all of that squared. So not
Okay,
much,
minus. Yeah, that makes sense.
no more complicated than what you saw here. Yeah, thanks.
Okay. And this recovers the Polacek engine formula and some limit.
Absolutely. So if you have a constant like work completion rate, so like in a GG1, for instance, then these delta A and delta C, these relative arrival and relative completions, they have a simple characterization in terms of the amount of work in service. And so you would exactly recover that formula up to the behavior when the queue length is empty, which is already a challenge when analyzing systems like the GG1. Thanks.
Thanks.
Yeah, question from Shane.
Thanks, Isaac. I have a clarification question and one, I think, more research related. Could we please just look at the formula that you obtained for the first formula you obtained, where you had three terms? So it's probably back about.
Oh, you mean for the two-level arrival system? Yeah, let me.
Yes, please. Yeah.
Okay.
Sorry to make you drag back. Yeah.
My computer just lags a bit whenever I switch slides rapidly. I'm not sure why. Okay, so this is what you're talking about.
Great, thank you. Yeah. I had this kind of impression in my mind that when lambda H and lambda L were close, that we would sort of descend towards the standard MM1 formula.
Yeah.
And when I look at this, is there some cancellation that's going to happen or something? Because I see these terms which are all subtractions, which would mean that everything goes to zero.
Right. So so something to notice. So when we went to prove our bounds, the scenario where the lambdas are equal is the area we can bound the least well. And the reason that's happening is exactly as you say, there are a bunch of cancellations happening that make it unclear. Okay, the more I look at this, the more I'm concerned I dropped the term that would dominate in that case. I think I may have lost the +1 here.
Yeah, I was kind of thinking there might be a +1 on that first term there.
Yeah, I'll double check it. I think this might just be this quantity here, and so it should be this parenthesis +1. So my apologies.
Yeah, no worries. I figured it was probably just something like that. And then I guess the real question that I was curious about, here you've looked at one kind of time inhomogeneity where you have this Markovian arrival process, but there's still mixing and you end up with a Markov process, so everything is kind of nice. Is there any hope that some of these ideas could extend to systems where the time dependence is regular, like on a weekly cycle or something like that?
Yeah, so I do think that is possible. The issue or the thing that makes those systems more complicated is that the limiting behavior of the relative arrivals of this plot here, it's never going to simplify out to a straight line, right? So
that's sort of true, but the kind of thing that I was thinking was you would extend the Markov process to just, point out where you were within each cycle, and then it's it has this periodicity which is a nuisance.
Exactly. So basically, your expected arrivals up to time t is never going to converge to a straight line, right? It'll converge to some regular variation around a straight line. So I do think that this method, potentially could be extended in that direction, and you can sort of guess what the function should be, and it does check out, but proving it, I think, will be more of a challenge. So yeah, it's an interesting research direction. Thank you. Ziv, you want to go next?
Yeah. Thanks for a great talk, Isaac. So towards the end, you said, okay, you can do this for both arrival and completion modulation.
Exactly.
Is there any, I assume that those were by independent Markov processes, and I was wondering, do they have to be independent even, or does it just work?
Right, it just works fine even if they're coupled. Yeah, instead of getting separate relative arrival and relative completion functions, you just get like one big joint, relative drift rate function or something like that. But it works fine if you do it that way as well.
Cool.
Absolutely.
So actually, I also have one question. There's a oh no, Steve, no, okay. So yes, I was wondering if you tried applying this formula to a larger system, at least a more complex system in terms of the arrival process, and if you saw anything that might become visible when you have a more complex process, for instance, that wouldn't appear in this particular case with the two-state arrival process, or?
So we have applied it to more complex systems. I think I mostly focused on more complex service processes, but as you can see, the ideas are the same. And essentially, so, this is something we look at a bit in the context of these multi-server job systems, because we're using these Markov modulated service processes to model them. Essentially, the main, so one thing I'm interested in, so basically these techniques will allow you to get, symbolic response time formulas for a fixed Markov chain of arrival rate or service rate. A direction I'm interested in, as I mentioned earlier, was trying to find results that, generalize over a family of related service processes in this sense. One sort of interesting part of this is in a relatively simple system, there's only sort of a relatively small amount of effect that these relative arrivals and relative completions can have. Like, they only move in one direction. So this delta H is just monotonically increasing up to this long-term rate. In a more complicated system, it might, bounce all over the place before it settles down to something. And that might give a more complicated behavior when the queue length is empty, for instance. But, essentially, it's all the same system, or it's all the same concept, at least at this level of viewing it, whatever your arrival process might be. Yeah, thanks.
Thank you. Any other question?
All right, I
So
have an answer.
Varun asked a
Oh, sorry, go ahead.
question on the chat message.
Oh, there's a chat question? Wonderful. Yes.
That was more of a, I guess, clarification, like on Shane's question when he was asking what happens if lambda and lambda are close. I assume if the lambda is bigger than mu, then you can't have both of them close to each other because you'll be unstable.
So I think, okay, so there was one bound where I used the assumption lambda h greater than mu, but for this part where Shane was asking about, there's no limitations on lambda h and lambda l. So it was in fact just that I think I forgot a +1 here.
Okay, thanks.
Yeah, this result holds regardless of lambda h and lambda l, whatever value they might have. Yeah, thanks for the question.
I have another question inspired by Celine's question.
Uh-huh.
So, could this sort of technique apply to a Jackson network where everything is Markov modulated? And, you know, you wouldn't necessarily expect to get a product form result, but could you, you know, in the same way, you wouldn't maybe know exactly what the Markov modulated arrival process to one queue was, right? Because it depends on how often the other queues are empty. But maybe you can bound things. Is this the sort of thing that has hope of working, or maybe not, or you have to think about it?
So sort of the danger with Jackson networks or other sort of objects that are more complicated than a single central queue is that you can get into situations where some queues are empty while other queues aren't. In this system, an empty queue can only have a sort of limited effect because if the queue's empty, there's no jobs in the system. So, you know, it can't be a huge influence on mean queue length. But in systems where you can have a ton of jobs at one server and another server is completely empty, now that becomes a lot more important. And you know, you're putting a lot more pressure on your ability to bound the behavior of those states. So it's not something I've had much progress with. That being said, one interesting angle is systems where you have some sort of network of queues, but all the stages except for one have a bounded buffer length. And then you have like feedback or something at the other queues. And these can be analyzed by this method, and you get pretty interesting results from them. And they're a pretty natural object that shows up in a lot of settings. So that's the direction I'm taking this.
Sweet. Thanks.
Absolutely.
Okay, so I think that we can conclude the seminar now. I think it's common that people can stay and keep talking to Isaac about the talk or about other questions. So thank you again, Isaac, for your very nice talk, and see you all in 2 weeks for the next SNAPP seminar. Thank you.
Yeah, thanks everybody for coming. And yeah, I'd be happy to take, you know, to chat about this further if you'd like to stay around.
Speaking of this, actually, I had, yeah, it's not really concrete, it's a bit vague, but you know, here in this, what you do is you want to estimate the mean queue size, and you use the value function to get a better estimate of this. But you know, you could think that maybe in some other systems, it might be the other way around, like there's some quantity of which you can estimate the mean value, but looking at the value function itself is difficult. So can you, you know, would it be imaginable to do it the other way around, like use a similar expression to get information of on the value function using mean value, or would it, maybe it wouldn't make sense at all?
So this relative value function is sort of designed to be very easy to characterize.
Yeah.
Because it only depends on the behavior of this finite size arrival process. it's sort of inherently going to be much easier to work with than behavior of the whole system. Now, I'm sure there are systems where it would have some complicated behavior. I just don't know of any. Although, you know, you could look at something like the like a known size system, you get some like huge exponential blow up of states, and it could be very complicated. But going in the backwards direction doesn't work so well because you only get this one, one piece of information of like what its value is at this specific distribution. So that's
Okay, I was just being curious.
Yeah, no worries. I mean, it's certainly an interesting direction. I just don't, I can't think of any systems where it would come up, but yeah.
So thinking a little bit more about the Jackson network question.
Yeah.
So I think what you said convinces me that this would be hard to do if you wanted to get like the joint distribution of all the things and try and prove some product form.
Okay.
You just wanted to know the mean queue length at each server individually.
Okay.
So basically,
yeah.
Then, you know, assuming stability, which maybe is an assumption, you know the average rates, and so you know what the rows are in all the queues.
Sure.
And then maybe by sort of, maybe there's some way to say, if a queue is like super empty a lot of the time, or like if you consider one queue, you have various queues that are feeding into it.
Yeah.
And maybe there are ways to sort of say, well, you don't know exactly what those processes look like. And in particular, they might be correlated with the output process of, you know, the queue we're focusing on.
Yeah.
But might there be ways to sort of bound it, and would bounds suffice?
Well, so okay, so what I'm seeing here, so it's like basically if you're downstream of a Markov modulated queue, right?
Yeah.
Then what does the arrival process to your system looks like? It's, you know, it's this weird mixture of that system's Markov modulated output process with its queue being empty process, right?
Yeah.
That's this like weird, hard to characterize function, which is why, you know, traditional Jackson networks are so cool, is that they can exactly characterize it.
Right.
Yeah, basically, if you can bound it, you get bounds on the like numerator of that. You saw the formula that I had, right?
Yeah.
You've got a 1 minus row in the bottom, you've got a numerator, and you've got like an additive term at the front. If you can bound the behavior output process, like how correlated it is and stuff like that, that's going to give you bounds on the numerator of that 1 minus row function, which is still more than we might know about these systems previously. So I think it is a valid direction. It's just not nearly as like clean or closed form as.
I see. Yeah. I was hoping that, maybe we only get bounds on the additive part, but I see what you mean, that there would be something in the numerator as well.
Exactly.
Harder.
Now,
all right.
If it's a simple enough, you know, for instance, if you have something like, you know, some simpler queue like an exponential or an PS or something upstream of a Markov modular queue, everything's wonderful, obviously.
Yeah.
But yeah, if you're sticking together multiple of these, I think it gets quite difficult.
Makes sense. All right, thanks.
Absolutely.
All right, I'm gonna head out. Bye, everybody.
Yeah. Cool. Yeah. Thanks, Celine and John for organizing.
Yeah, thank you. It was really educative presentation, I think.
Yeah, excellent talk.
Yeah, thank you.